The atom. Early theories. John Dalton first stated that atoms are indivisible, indestructible spheres. J.J. Thomson proved atom was divisible by discovering the electron. He made the plum-pudding model of the atom, which had electrons embedded into a positively charged mass. Ernest Rutherford proved plum-pudding wrong using the gold foil experiment and created the nuclear model of the atom, where most of the mass is combined in the center of the atom, called the nucleus, which electrons continuously orbited. Bohr realized that constant motion of electrons should have created constant radiation in the form of light, and an electron should have eventually crashed into the center of the atom, collapsing it. So he made an atomic model for hydrogen, stating, electrons exist in circular orbits which were quantized, and electrons could transition from energy levels. Schrödinger used de Broglie's idea of matter waves with his wave function, and then created the quantum numbers, which refers to the orientation of the atom, and created the new quantum mechanical model of the atom. Units of measurement include atomic radii, which is half the distance between the two nuclei of two adjacent atoms measured in nanometers. Ionization energy is the energy required to remove an electron from a ground state atom in the gaseous state. The unit used is kilojoules per mole for chemists, and the electron volt is used by physicists. Electronegativity is the relative ability of the atom of an element to attract electrons in a chemical bond. Atomic mass unit used to mass subatomic particles in U units. Quantum theory or quantum mechanics. Quantum theory is the theoretical basis of modern physics that explains the nature and behavior of matter and energy on the atomic and subatomic level, and explains why light behaves as both particles and waves, and why particles like electrons can act as waves. In quantum mechanics, a particle does not have an exact position but can be considered to be in multiple positions at once. A wave function is an equation that describes the probability of a quantity having a certain value. When we measure the position of a particle, the wave function collapses into a simpler one that represents a specific position. We have changed the nature from a wave to a particle. Source of wave-particle duality. The wave in the picture can be seen as an electron wave surrounding a nucleus, which is the field. The wave is continuously moving, and each person is where an electron could be at that moment. Once you find the position of an electron, the wave is broken and just one person is there. This leads to the Heisenberg uncertainty principle. Delta x times delta p is greater than h/2. This basically means you can only know one thing about a particle with precision. This led to the development of flat-screen TVs, sensors and digital cameras, and lasers and DVDs and Blu-ray players. Matter waves. Einstein's photoelectric effect experiment showed that light has both wave and particle characteristics, and he proved that light has packets of energy of a particular size called quanta. These quanta can collide with atoms and can be absorbed by them. De Broglie suggested that not only do waves behave like particles, but particles can behave like waves. Wave-particle duality is a single entity exhibiting both wave-like and particle-like properties. He suggested that matter had a wavelength, so he created the Broglie wavelength equation. Lambda equals Planck's constant over momentum. Momentum equals m times v, so Planck's constant over mv. Take a grand piano, throw it down the stairs. Piano is 400 kilograms, falls at 2 meters per second. Lambda equals 8.3 times 10 to the power of negative 37. This number is very small and cannot be visualized in real life. So the grand piano is too large, but an electron can act as a wavelength. The de Broglie wavelength of an electron is small enough that you can observe wave properties. This is used most famously in the electron microscope. This microscope bounces electrons off the atom, observing diffraction effects as it does, and uses the path of the electrons afterward to create an image of the atom itself. The photoelectric effect. The photoelectric effect is when a metal releases electrons when the light is shown onto it, and this happens because energy is transferred to the electrons from the light. Heinrich Hertz is the first person to observe and publish observations of the photoelectric effect. He realized that when light was blocked from a spark gap, the sparks did not occur as often because electrons were given energy from the light, which allowed them to be released from the atom. Leonard observed that brighter light released more electrons and a higher frequency light released higher energy electrons, and due to this, Einstein realized that light must contain packets of quantum energy called photons, and noted that the amount of energy depended on the frequency by the following equation. E equals hf. So the brightness of light only determines how many packets there are and how many electrons can escape, not how much energy the electrons have. The best application for the photoelectric effect is the old television. Electrons produce a fluorescent screen that emits light. By controlling the electron, you control the image. Radioactivity. Becquerel discovered radiation when he put fluorescent salt into photographic plates covered in black pepper into a drawer, came back a couple days later and the pepper was covered in light. The salts continuously fluoresced without an energy source. Marie Curie was able to note that uranium electrified the air around it. She discovered uranium, polonium, thorium, radium. An isotope is an atom of the same element that have different numbers of neutrons. When isotopes are unstable, have imbalance of neutrons and protons, they are radioactive. Carbon-12 and carbon-13 are stable because number of neutrons and protons are in good balance. Carbon-14 is unstable because it has too much energy and eventually the extra energy will be released, called radioactive decay. After enough energy is released, it will return to the stable atom. Half-life of a radioactive material is the time it takes for half of the unstable nuclei to decay. There's 3 ways an unstable nucleus can decay. It can give out alpha particles, which is 2 protons and 2 neutrons, the same as a helium nucleus, or beta particles, when an extra nucleus turns into protons, which releases a high-energy, fast-moving electron, and gamma rays, high-energy electromagnetic radiation. When radon emits an alpha particle, it decays into polonium, and carbon-14 decays into nitrogen when it releases the beta particle. Mass-energy equivalence. Mass-energy equivalence is basically the idea that mass and energy are really the same thing. If you increase an object's speed, and therefore energy, you also increase its mass. This is why it is impossible for an object with a mass to go faster than the speed of light. As you get closer to the speed, you increase the object's mass, and if you increase the object's mass, you make it harder to give it more speed. The equation for relativistic mass is equal to m over 1 minus v squared over c squared, all square rooted. M is the rest mass, and using this equation of special relativity, Einstein concluded that the total energy, so E total, for an object with rest mass, m, is moving with speed v, is equal to E total equals mc squared over square root of 1 minus v squared over c squared. When an object is at rest, the equation simplifies to energy equals mc squared. The rest energy is the amount of energy with respect to an observer. Relativistic kinetic energy is the difference between total energy and rest energy. So E total minus E rest equals EK. Conservation of mass energy states rest energy is equal to m rest times c squared.